With that, I want to introduce James Young from ETS-Lindgren. So he's coming in from Texas, so I'd like to welcome him. And a little background about James. He's a Director of Business Development at ETS, and he has a background on electrical engineering, RF testing, EMC testing, and has worked in our industry for over 20 years now. Prior to ETS-Lindgren, he was Director of Sales at Amitech and also at Roden Schwartz. So with that, let's all welcome James. That's
right, because the laser gets lost. Oh, it will come in.
Barely.
Barely. All right. So before I begin, I gotta make sure. Are there any RF device test experts in the room? Good. All right. Because I don't know this much. I don't know this well. So I'll give you the high level stuff. But if you guys are going to deep dive, I need to change presentations. All right. So 5G is all the buzz, right? We're getting a constant media bombardment about 5G. Let me back you up a little bit and tell you what the standards committees think 5G should really be. So first off, there's this consortium called GSMA, and they boiled it down into these major topics. This is the CEO of Ericsson. His company's going to make all the base stations that talk to our phones. So I grabbed his slide. But really what it says is they want to allow gigabit per second connections to your mobile, whatever the user device looks like. They want to decrease end-to-end round trip time to 1 millisecond. We'll get to this. Connect at least 10x devices to the network compared to where we are presently. Provide this perception of 99, 100% coverage, 100% availability. Decrease network energy usage by 90%. That one really caught me off. And enable a multi-year battery life for a low-power like machine device, IoT device that sits out there. So that's what they want 5G to look like, or to be. And you know what? We can ignore a good chunk of these goals. So let's just throw some of this crap out first. Network energy usage by 90%? No way. We're only going to get bigger, because now we're going to need 2 sets of radios on every tower and many, many more towers to provide coverage. So there's no way they're going to cut that down. 10 to 100x devices connected to the network. IoT will allow this, so yeah, okay, I can buy that one. Availability and coverage, that 100% perception of availability and coverage. Well, that's really, we're talking signal bars at that point. And that's a factor of how fast, how quickly they can return the investment. Their metric is that ARPU. That's average revenue per user. If that is there for them, they will build the networks. The Verizons, the AT&Ts will build out the networks. If it's not, they're not going to do that. Battery life, well, that's totally dependent on implementation of the hardware. So we will have no impact on that. So we can just throw all these out because we don't care about them. There's another one of those that I think is unrealistic, and that's the latency to 1 millisecond. That's round trip time, 1 millisecond. Let me tell you why. To decrease the latency, essentially everything from the base station backwards into the internet has to be rebuilt. Now think of the infrastructure that we're talking about. Every fiber connection, all these bounce arounds, and I don't even know what all these acronyms are, but essentially everything from the cell tower back to the network, Verizon's, everyone will just have to be rebuilt to decrease latency. And there's no way that the ROI, the return on investment, is there for them to reduce that. Also, I think 1 millisecond is an incredibly hard goal to achieve. Some of the things that they've talked about doing with this 1 millisecond latency connection are remote surgery. You go first. I'm not going to have some doctor, you know, who a continent away working across a network connection to do my surgery. So the other thing that I've heard is car to X, car to car, car to base station, car to traffic connection, whatever, car to something. And even as fast as we drive in Texas, at 87 miles an hour, you're only driving 1.5 inches in 1 millisecond. That's pretty hardcore resolution for an autonomous car. I just don't see why they would need it. You can get away with probably an order of magnitude less resolution there. Another one, AR and VR, that's virtual reality, augmented reality. The revenue has to be there. If there's a killer app other than cat videos out there that drives this, maybe, but I don't see it, not yet. And then the AI that everyone's talking about, you know what, unless you're processing, unless you're capturing here and then moving it off somewhere to be processed and then moving it back, latency really isn't the biggest deal with AI. So really I just don't see where that latency, that 1 millisecond thing is driven from a revenue standpoint. Again, it's going to be chicken and egg here, right? Something's got to come out to drive the infrastructure guys to replace all of this. Otherwise, we're just not going to do it. All right, so then gigabit, we're left really with this gigabit per second connection that we want to drive down to our mobiles, hockey pucks, whatever it might be. So again, this is cat videos. You know, how much data do we really need? They're assuming that if they build it, we will come up with something. So let's assume they're right. Let's assume that we all need some killer app comes out and we all need this gigabits to our mobile device. All right, so they're going to do this in two ways. First of all, they're going to rebuild what we call the sub-6 gigahertz section of all of the towers that are out there. This is the present network, the LTE network, 3G network. They're going to rebuild that and add some really cool radio technology, antenna technology. Get into that in a second. The other thing they're going to do is they're going to move way up in spectrum into the millimeter wave. So this is 28 to about 60 gigahertz. It's called FR2. There's your buzzword for the day. FR2, frequency range 2. FR2 radios, millimeter wave, what they can do if they move us way up there in spectrum is they can open up 3 gigahertz of bandwidth down to your phone. Then they can split that up between all the users. So if you guys remember Shannon-Hartley theory from school way back, you can only mess with a few parameters here when you're trying to increase bandwidth and capacity. Sorry, increase capacity. One of them is bandwidth. You've got to have bandwidth, and the other two are signal and noise. Either you can increase the bandwidth, you can increase the signal power you send, or you can decrease the noise. Those are the only network parameters that we have to deal with. And so something's got to give. Noise, you can't control so much. Signal, the more signal you send down, the more you interfere with other people. So they went bandwidth route, but went to spectrum. Okay, so keep in mind these two splits because we're going to talk a lot about them now. First, I'm going to go off on that sub-6 gigahertz. This is what you'll hear. Remember I said buzzword was FR2, frequency range 2? Well, sub-6 is frequency range 1, FR1. So whenever you hear people talk about FR1 radios and FR2 radios, that's the secret code that they're talking. All right, so first thing they're going to do is they're going to roll out something from the military that's been used for decades. It's called MIMO. It's actually called beamforming. We're going to apply it to MIMO. So beamforming allows you to steer a beam, a narrow beam, to an individual user. Military guys use this on radar. They use it in their special comms systems, and they can actually direct a beam to a particular user. Why would you want to do that? Well, first of all, you the more power you send to everyone else on the far left, that power looks like noise to those other mobiles. So if you can drop the noise, blacken the field if you will, and still get the signal that you need to a particular user, you play with that signal to noise ratio. That's a great win. Massive MIMO is the ability to do that on a big scale, hundreds of devices. So we steer a beam to the devices that we need. And this, as rocket science-y as it sounds, is actually done in the military already. We're going to just apply it to our existing network. And here's the Wikipedia poll about this beam forming, if you will. It's pretty crazy stuff, but someone way smarter than me came up with the fact that you can phase shift a bunch of antenna elements. Even though up close it's a very spherical wave, as they get out further and further, they combine into a plane wave. And out here then, you can actually use the phase shift to steer the beam. Then if you lay that down on its side, you get the same thing in the other direction, and all of a sudden you really can steer a beam in 3 dimensions. This is a really fascinating wiki page if you want to pull that up, by the way. Okay, so now how do we apply that to a test environment? ETS-Lindgren builds the chambers that most people are using for this, and so I'm always trying to figure out how do I build that environment, that controlled environment for you to test this. Well, so first off, you've got to know the physics of this. Remember, I said that at a distance, these waves start to look like a good, predictable plane wave. That's called the far field of our antenna. And for a MIMO setup, for a phased array antenna, we have to factor in this range is 2d squared, with d being the diameter of the antenna array. I don't care what your device size is, I care about what your antenna array size is. Now at sub 6 gigahertz, 2.4 is kind of in the center of everything that we do in the US. 2.4 gigahertz, if I have an array that is 2 meters in diameter, I have to build you a 64-meter chamber in order to be in the far field. Anyone want to sign up to cut the PO to that one? That's going to be a multi-million-dollar chamber. There are facilities out there doing this. Most of them are not enclosed. There are a few out there that are this big, but not very many. Also, I have to be able to, it has to have height as well, because I have to move that antenna around and to test what your beam is really doing inside that chamber. That's a complicated scenario. Here's a kind of an idea of how we accomplished it. It was one of the base station manufacturers. We actually built a curved wall and exploded the antenna elements out, and then moved a device under test that represented the UE, the user equipment, around so that you could see if the beam could follow the user equipment as it moved across the array. This was a big chamber. You'll notice there are many positioners on both sides, because essentially we were trying to test that things were moving like they should. And so that's what we spent a lot of positioning time doing. So again, big chambers, lots of positioning, and probably not your typical solution here. This is going to be for the Ericssons, the Nokias, the people that are building Huawei's, the people that are building the base stations. I saw a question?
Yeah, is that the large chamber, 60 some odd feet or whatever, or was that?
It's really not that big. By curving the wall and
So
doing some other things, we were able to reduce the
Okay.
size, but it was still a big, big project. Okay, now we're going to go the other way. That was that sub 6. All the fancy stuff we're going to do on the radio side. There are lots of other things that are happening, but from a test standpoint, MIMO, massive MIMO was the big one. Now we go from sub-6 down to tiny stuff. At millimeter wave, the 25 gig to 50 gig, let's just call it into this. Everything gets tiny and everything gets integrated. This is the Qualcomm integrated 28 gigahertz antenna down conversion and processing module. It talks to their new X50 modem here, and you can see the size. What will happen, I didn't bring my, yeah, there it is. What will happen is they'll take this module and they'll put it edgewise on your phone, probably in 3 or 4 spots. And then when something like this happens, when you grab this way, other parts of the antenna will take over. And steering the beam allows, as you move around, it to still steer and try and talk back to keep the connection, the gigabit per second connection, back to the base station. And imagine the amount of processing and work that has to take place for that to happen, especially if we're in a car or walking down the street. The other thing to know about this is there are no cable connections available anymore. We cannot cable a MIMO antenna, a beamforming antenna on this device. Number one that gets us is the size. Number two, remember we have to be a certain distance away from this thing before that wave looks like a plane. So even if I could connect onto the individual little dots of the antenna array, I only get one piece of information, and the fact that we're steering a beam, we need the whole array transmission in order to even begin doing testing. So we're used to, on the left is a typical cell phone antenna that we get now. We're used to having a little connection, a little RF connector. Has anyone worked with those push-on, what are they called, SMCs, SM somethings? They are a pain. They bend, you don't get them on there right, they pop off. Well, the good thing is you won't have to deal with them anymore. The bad thing is there's just no way to even deal with it. So we're also going from an omni to a narrow beam that's moving around. So the testing just went up an order of magnitude in complexity. All right, how are we going to do this? How are we going to test this? First of all, the first stage for R&D, any of you in the R&D phases on these mobile devices? No? Okay. For the R&D guys, first thing is you got to figure out how to replace the cables. You'll need some sort of a link box, something to isolate from the outside and connect the two devices that you want to test. So it can be something as small as a shield box, just that would fit your device and give you the separation you need. If you want to manipulate it without touching it, you might need something a little larger with the positioners inside. But depending on your link and what you're trying to accomplish, you will need something that replaces the cables. One other piece of data to go on here, compared to cables, we're used to dealing with a quarter or maybe a half a dB of loss. We start at 20 dB of loss with these links, and it goes up from there, depending on how the distance really clobbers us here. So 20, 25 dB of free space loss between the device who's transmitting and the antenna who is receiving is not going to be uncommon at all. So you've got to wrap your mind around the fact that we're dealing with much higher loss characteristics. Okay, so in order to even begin, again, just R&D phase, just cable replacement. This is protocol guys. These are guys who aren't even concerned about the antennas, aren't even concerned about the RF characteristics. What happens is you grip the phone a different way. They're just simply the chip-to-chip stuff is what they're concentrating on. This is where they'll stay, in just replacing the cables. those of us who have to quantify all these other parameters, you know, walking through the room, how does this device do this? Grabbing it, different methods, what happens to the antennas, what happens to the link, what happens between antennas. So Wi-Fi plays nice with Bluetooth, plays nice with millimeter wave, plays nice with sub-6. All of those things are going to require an environment with a very controlled set of parameters. So 3GPP leads the standards bodies on issuing this information for us. 3GPP has a technical report called TR 38.810. Just a little light reading for your midnight, for your nightstand at bedtime, right? So what they did is they went in and said, okay, what we want this environment to look like for all the other tests, protocol conformance, acceptance, carrier acceptance, all these other tests, we want it to have multiple angles of arrival. So we transmit from various antennas. We want it to be able to move axis of rotation in 2 dimensions. And we want to be able to fade between one link and another. That would be to simulate like a handoff from one base station to the other. And so we built straight out of the, this is the figure straight out of the standard, and this is what we actually built to conform to it. And it's a complex beast. I said, where did all your lab space go? Well, I just took what most labs were doing with a cable and a small connection, and I turned it into this.
How big physically is that?
It's about a refrigerator, a little bit larger width than a refrigerator.
Would you need a bigger one if it was like the base station?
Yeah, exactly. Base station gets really complex because we're doing lots of, the antenna array, remember the antenna array is what matters. I don't care about how big the device is, I care about that antenna array, and that dictates the size of the range. So yes, base stations get way bigger. We'll lead into that. Okay, so how are we going to do this? All right. Before I go on, I just want to point out how complex this is going to be. Okay, so far field calculation. Again, I don't care about the device size. What I care about is where the antenna is on that device. From the antenna to the receiving antenna, I calculate the range. Well, now I have 4 antennas on this device. What happens when I rotate it? That range changes by double even. It changes all as I start moving it. It's going to be really fun. We're used to about half a dB of measurement uncertainty. We call it ripple. When we calibrate a chamber, that's our figure of merit. Anything more than half a dB of ripple inside kind of says, we need to go look at the positioners again. This is going to be orders of magnitude more. And I don't know how to wrap my mind around it as a test guy, right? What we're going to come up with. But I left this and I took it out on my other presentation. It really does matter. Let me show you how much it matters. So the red and the green are, the red is the typical. This is no interference. The green is a person off in the corner of a chamber, essentially. What we did is we put a phantom. You guys know phantoms? The heads and the hands and things that you stick inside these chambers. Stuck a phantom in there, and it affected it a little bit, especially over here where the phantom was. So the green versus the red. But then, for the blue, we actually put a real person in the chamber. And look at how the entire, this whole side just collapsed. The main beam, especially, 1/2 of it is gone. And the whole back section of the array is almost gone and collapsed. So green and red, well, sorry, red versus blue was a massive collapse of the field on one side of the device under test. So this does matter. This is going to
Right, it does matter.
It does matter.
This is all absorption?
Yes. We think the market will go past. So what I'm going to do is I'm going to tell you the next few slides, the environments that the 3GPP standard have laid out as standard environments, what you should use. We think it's going to need to be more complex, at least for the true device integrators, whoever you are, you know, the Apples, the Samsungs, the people that we pay for these phones, you know, $1,000 every 2 or 3 years. Those guys will need something that will quantify what's happening as I rotate this guy, and it's going to take a more complex system than just what 3GPP has laid out. We think it will end up being something like this, where you know, we're not just focused on the main beam. We want this guy to steer. We want him to steer around obstacles, or when I put my hand here. Well, 3GPP has said, just ignore the steering. We're going to lock down the beam and just focus on the main node, and it's just not going to be good enough. People are going to want to know what to expect out of the device when we're doing things, when we want it to steer. So we think that a complex positioner like this will be needed. We actually have a patent on this. So we can move, we can probe, these are receive probes. As we move this, we also try to track the steering beam. That's what we think it will turn into. But 3GPP has said, okay, we've got to start somewhere. Where we're going to start is we're going to define 3 scenarios. First scenario is just one small millimeter wave antenna array up in some corner of the device. Scenario 2, configuration 2, is 2 devices that are working together. They're coherent. And configuration 3 is a much larger antenna array, like over a good chunk of the device, or maybe a base station or something of that nature. And they say, okay, so as long as we lock down these 3 configurations, what sort of an environment will return some usable information? So another table, they said there are 3 methods. Direct far field, indirect far field, and then a near field. We're using a software transformation. Okay, these are pretty typical. Anyone heard these things? This is straight out of antenna theory. We build the same sort of environments regardless of the application, because these are what work, right? We would love to build direct far field chambers everywhere, but they get really big. Indirect allow us to get a little smaller, and near field gets really small, but then a lot of other things go wrong. So, 3 acceptable test methods, and what do these look like? Okay, first off, the direct far field method, and that's your typical chamber. You've got a device on one side, you got a receive antenna on the other, you maneuver the device around, and you draw an antenna pattern. For a 5G device, this is our solution, and it is nearly identical to the size of this table, or the table that's in front of you. So it would sit on this table. Door here, receive antenna on the other side, and then the positioner inside there. So this tall, that long. But again, what are you replacing in your lab with those devices, and how many of them do you need? What's the throughput? How long will the test take? These are a lot of parameters that we don't quite know yet. So your lab space, maybe just got a little smaller if you need these. Okay, so direct far field, the pro is that it's simple construction and it's known art. We've built thousands of these. The con is that, again, we're back to this free space path loss. We're starting at 20 dB, and it goes up pretty fast from there. So then link budgets and things get in the way. We have to really be careful about how we do that. In order to get a larger quiet zone, like if the device was in configuration 2 with 2 antennas spaced apart from each other, well then that means I have to expand the quiet zone, which may dictate a larger chamber. And that's a D squared, so as D goes up, the chamber gets large very, very fast. So easiest to build, easiest to work with, probably the cheapest solution, but you have to have the right device in order to be able to use direct far field. Okay, indirect far field. So this is crazy. Really smart people came up with this. Essentially, we use a reflector or a lens to, in the near field, to bend the signal so that it appears as a plane wave by the time it gets to our receive antenna. So receive antenna here or here. So the device either, well, it works in reverse as well. In this case, the device is sending, we're collapsing and feeding it to the antenna. Or the other way around is the device is transmitting, we collapse it in here, or it also works in reverse where you transmit from this antenna, it hits a plane wave, and then we can test the receive antennas on the device, the receive sections. So here's a better way to simulate it. The simulation actually shows you how this works. If we transmit from here, we bounce off the reflector, and by the time, in a very short distance, we have a nice plane wave that we can test. But these reflectors are very expensive, take a lot of engineering, and very complex to build as well. So one of the cons is that the indirect far field tends to be more expensive. You can do a larger quiet zone in a smaller space. To Gabe's point, the base station guys, maybe so a millimeter wave base station is probably going to be, you guys have seen the control boxes that are mounted on light poles, for instance, traffic signals such as that. You know, that's probably what a millimeter base station is going to look like, about this size. The antenna is going to be mounted right on the metal box, or whatever the box looks like. The equipment, the electronics will be inside the box, and they will have to deploy millions more because a typical link for a millimeter wave station is like 1,000 feet. So nearly every couple of street corners, we're going to need one of these base stations versus a typical 4G LTE base station tower covers kilometers of people, of devices, of connections. So if we need to get a base station into a chamber, we probably need an indirect far field method. But again, they're expensive, and anytime that I adjust something, I have to make adjustments inside the chamber. So, for instance, now you'll see a lot of rails here. Anytime you change frequency or device or how much things are moving, you have to adjust the back and forth of both this antenna and this, and also the angling. So your test setup takes a lot of preparation to get right and accurate before you can actually start testing. So indirect far field may work for some, may not work for some. The last method they announced was near field, and this is a nice compact chamber. We only have to be 2 to 5 lambda away from the device. Lambda is wavelength. then we turn it over to software. So we make a bunch of measurements, we step that probe around or move the device very carefully, and then the software takes over. And the software, knowing all the parameters of the transmit and of the receive and of the path, can make this fancy thing spit out that tells you the antenna pattern. We do not make the software for this. We don't offer this method. There are a few people around that do, but the big thing to know about this one is that it's really a transmit power only. There's no receive or quality tests that are available here, because when we're using QAM, right? We're using amplitude modulation. So in the near field, AM it doesn't behave in the same way that it does in the far field, and so things get very complex very fast. So essentially, there's no isotropic sensitivity, there's no blocking quality tests really of any sort. It's just going to give you a transmission antenna pattern out of a near field to far field transition system. So you got to factor that in. Does that work? Is that enough information for what your lab might require? All right, so the conclusions for those of you who need to make these tests happen. Remember that, especially as we go into 5G, whether we're talking about sub-6 or millimeter wave, there is no way to separate the antenna from the electronics that have to drive it. It is a smart antenna system. So you cannot plug onto an RF port and get data anymore. The antenna is part of the equation, like it or not. All the radio tests, not just initial, what we're used to is just antenna pattern measurement. Now everything, clear back to the most simple R&D link between the device and a base station emulator, needs some sort of an environment to create that RF link to connect the devices. So functional tests might need just a, think of production lines. Any of you deal with production lines? Functional test, just simply I built the device, does it work? Do all the things work? You're going to need some sort of a link, RF link between the base station emulator and the different parts of the radio that we're used to doing as it's built up by a bed of nails coming down and touching it. Can't do that anymore. Even protocol guys will need some sort of a angle of arrival environment in order to test that the chip is behaving the way that it needs to. The enclosures use significant space. You do need to plan, you're replacing a cable with an environment, with a chamber of some sort. And also plan that these are very complex environments. So there's some extensive setup that needs to be worked on before you can ever begin the tests. They haven't even, 3GPP has not even addressed production yet. So we really have no data to give you yet on what they might accept as production. I think what they'll do is they'll just punt this one back to you guys as manufacturers or testers or whatever part of the equation you play, and they'll say, figure it out. You test what you think you need to in order to feel confident shipping the device. So the standards are just forming up. There's a lot of things we don't know yet. I think that most people are going to want to know what happens as the antenna, the AAS, the automatic antenna system. I've got the wrong word on the first one, but adaptive antenna system. As you move this around, we want it to react. We want it to steer a beam and try to hold up the connection. They're going to want to quantify that. 3GPP has not even addressed this yet. They want you to lock it, test here. Okay, now move it, test here. Now move it, test here. That doesn't tell us much. We want the device to be smart. We're telling it we're paying thousands of dollars for a smart device. We want it to be smart. So we need to quantify that. And the end one, really, the fact is, those of you who work in the industry, I'm getting a lot of people saying, we're late to 5G, we're late to 5G. There is no party to be late to yet. 5G has arrived for the marketing departments, for the Verizons and the AT&Ts and everyone who says, I've got to be first, I've got to have something to announce. That's all marketing. For instance, let me give you a true fact. If you go on the Verizon website, right now you can, in certain cities, order a 5G, it's a fixed wireless device. Essentially it is how many of you have fiber to your home, like a Fios or what do they call it now, Frontier? It's a replacement for charter cable, for whatever the internet service you have into your house. That's what they want to do. They put it out on a light pole, give you a little hockey puck that sits inside your house. That doesn't conform to the standard and won't be able to be upgraded. So that is considered just a marketing spend at this point. They don't think they can upgrade it. Yeah.
They actually do say that they will be replacing the hardware with 5G compliant once the standards.
Once the standards come out. So again, Verizon deemed that it was good enough to be first, that they were willing to send out some hardware that they knew that they would have to dump in a dumpster eventually, and reissue you compliant hardware when the standards form up and everything. So that's a marketing spend, and that's 5G has arrived for them and the marketing department only. For the rest of us who have to build these devices, who need to test them, who need to get all the bugs worked out, 5G is not here. We still have some time, and it's going to take some investment to get there. All right. So, any questions? Any other questions? Yeah.
You talked a lot about sensing signals, which could come from multiple directions, but nowhere, I don't think, have you talked about isolation or immunity from signals that you don't want, that are trying to get in and affect your product or affect the product being tested. So what are you going to do about security?
Security is going to fall to the manufacturer of the device. So you're talking about someone trying to hack you with RF or something? That's outside of what those of us who buy the devices can control. It's going to fall back to those people who build it. And that is, so it's not as easy to do that via RF. They will need to build protocols that sense that and lock it out. It's a protocol thing that we won't be able to control, but it does happen. Where I thought you were going to go with this is how do signals from the outside mess up the
That was
test?
part of it, right?
And in that case, this is a shielded environment, so it's a big metal box that we once we close the door, you have about 100 dB of shielding from whatever is outside of the room. So that part we can control. But if someone's determined to spy on or hack into your device, that's going to be something that Apple needs to differentiate itself with.
There might be a separate standard for cybersecurity on this.
I wouldn't be surprised to see that. Yeah, Ron?
As far as multiple devices at the same time in the operation, are there any standards that talk about that? So you have like multiple phones in close proximity, how the beamforming adjusts to?
So the only thing that we've done so far to address something like that is this sort of a big chamber with multiple positioners. So in that case, what we do is we put multiple phones and multiple base stations and then twist them around, move them around and see how they play together. Hugely complex, and these are all R&D things. There's no standard that defines how this all should come together, so that's really an R&D phase. Yeah?
Yeah, you talk a lot about UEs, right, testing, but how about, let's say, I know it's very early to talk about that, but, you know, an IoT device that is not a UE, let's say a medical device, can you comment on how different it would look like?
So we have to be careful about our terms here. UE is anything, really the system that we're talking about is a one to many, right? The one is the base station, well, that's what we just always call that, and the many are user equipment, whatever form they take. So if it's an implantable device, medical, if it's a phone, if it's a fixed wireless, if it's a machine, something, we just generically call those user equipment, UEs. So really the only two things that we have, actually that's a good point also I didn't talk about. IoT, Internet of Things, and 5G will go like this, because that's probably the network they're going to use. And so then again, you do not care what is happening on the user side. If it's processing data from a heart, from a machine, from your phone, from your voice, from your computer, we don't care. It's simply something to convert packets, to convert whatever analog into packets to send to some network somewhere. Okay, so I don't know how to answer your question.
Well, my question would be, you know, this type of testing that you mentioned, beamforming testing things, would that change if it was a medical device like a, you know, a pump or something?
I don't think so. You're still going to want to know. So you probably wouldn't do millimeter wave on an implantable device or a medical device. I would think you'd stay sub-6, but again, who knows where it will take us. The reason I don't think that is just because of the distance, right? You've got 1,000 feet distance, probably max with 5G millimeter wave. Anything more than that, away from whatever the user is and whatever the base station is, then you're back to the sub-6 gigahertz network that we have now. All right, any other questions? Good questions? Oh, yeah.
In the case of beamforming, currently how are the user equipments doing this? Are they doing this in baseband, the phase shifting, or are they doing this in the analog right before it's going to the antenna?
So, yes. There are baseband fading, and what we're really concerned with there is called pre-distortion, right? So we want to make the signal the best it can be when it hits the antenna and is sent out. And if we know what the antenna looks like and its pluses and minuses, we can pre-distort the signal so that when it does hit the antenna at the RF stage, it goes off and it's as good as it can be. So that's done in baseband. Most of beamforming though is done at RF, and we use a phase, or well, it's probably IF. We're using phase shifters. So phase shift between, call this a 64 by 64 grid of a base station array. It's probably going to be about this big. We phase shift between all the elements and steer the beam that way. But that's IF or RF.
So is the beamforming also going to be in the, you said it's also going to be on the UE side, right?
Yes.
So the UE won't have, the digital pre-distortion is probably for other characteristics, but for the beamforming itself, like you said, in the UE, sometimes there might be 4 antennas.
Mm-hmm.
So all the beamforming is happening at the antenna level,
Mm-hmm.
or, okay.
Yeah, again, back to the Qualcomm picture. Oh, I went too far. So there's a chip that rides on the back of this. So the antenna array and the processing, I believe this connection between the modem and this chip is probably IF.
I see.
And so then there's no way to distinguish what's going on inside of there. Therefore, it's got to be IF to RF beamforming going on. Any Qualcomm folks here? I don't know the Black Magic. I'm sure it's closely held and patented up the wazoo, but that's what they claim it will do.
And if we have one last question, then we're gonna take a break. Any more questions at all?
If there is, and I'll ask another one. The round trip time you said was charted to be around 1 millisecond.
That's what they want.
That's what they want. Just to get some perspective, what is the round trip time for LTE?
Oh, I do not know that. Anyone? I would guess probably 100 milliseconds or so. That's just my guess. Maybe even more. Depends on where you live and what connection. LTE especially changes its modulation the closer you get to the base station. So you can, if you're close to the base station, you can go up to 64 km, and then your latency is much lower than if you're further away. So,
Higher data rate.
Yeah, exactly. Higher data rate.
So with that, thanks so much, James.